Hello, I'm Ward Ramsdell, and I'm an electrical design engineer, consultant, and co-owner of Prototype Engineering. Today we're going to use the Tektronix MDO4000 to look at the system operation of a wireless audio system-on-chip IC. So what I have here is the evaluation board for the IC. It has a number of analog inputs. It takes those, converts them to digital, transmits them over the air to receiver devices throughout the home. Uses antenna diversity. In this case, we're using a couple of small monopole antennas for communications. And what we're going to look at with the MDO4000 is a number of different aspects of system operation simultaneously. We're going to look at the analog audio, digital audio, serial peripheral interface, and also the RF performance of the IC. And the scenario that I'm going to show is a frequency change command, where I've commanded the system to change frequency via the serial peripheral interface. I'll trigger on that and show the other aspects of system operation and show that they're uninterrupted. So now I've connected the wireless audio evaluation board to my complete bench setup with 2 digital buses, an analog connection, and then the over-the-air RF connection. I'm using an antenna on the front panel of the MDO4000 to receive the signal from the wireless audio system. That way I can see all the nodes in the system. I can also see the entire RF environment, including any interferers or other adverse RF circumstances. The scope is triggered. This is my original frequency. You can see I'm in the middle of the band. I use the pan knob to shift my spectrum time over to the new frequency. And I did see an interferer pop in there as well when I was navigating around, one of the consequences of working in a live environment. So here's my second frequency, the high channel. On the top trace I have my analog audio. Middle trace is my SPI bus. Bottom trace is my digital audio bus. And I can use the wave inspector functionality of the oscilloscope to really dig deeply into the data that I've captured. So what I'll do is I will turn that on, zoom in around my trigger event, and I'll actually be able to look at the SPI command for the frequency change. So 16000200, that happens to be the last 4 bytes of the packet that were sent to change the system to channel 2. If I zoom in more closely, I can even see my analog or my digital audio packets right and left as they're being transmitted across. So what this has allowed me to do is get a very good window into the operation of my system. I'm looking at the system's operation on about 4 different fronts, and I'm not even thinking about the data that I'm capturing. It's all just going into the instrument, and I'm seamlessly moving back and forth between the analog measurement, digital measurement, and frequency domain measurement, all in a time-correlated fashion.